last lecture, I told you how to add angular momenta, and so we demonstrated how to start with two spin half objects, for instance, and add them to get coupled states which are either spin triplet states or a spin singlet state. So we will continue with addition of angular momenta. And yesterday we worked with J1 equals half in units of H cross, J2 equals half, and this gave us coupled states, the spin triplet state. By spin triplet I mean J is 1, the third component M is 1, J is 1, M is 0, and J is 1, M is minus 1. This is the triplet state of angular momentum, and if indeed by J1 and J2 we mean spin, then it is the spin triplet state. And we can have a spin singlet state as well, that is just one state with J equals 0 and therefore M equals 0. We also learned how to write this coupled state, coupled basis states in terms of the uncoupled set, and we had the following. Suppose my notation is J1, J2, Jm for the coupled basis. J1 and J2 are anyway fixed as half and half. J is 1 and M is 1. Now this state can be written in terms of the uncoupled basis states. The uncoupled basis states are represented by J1 M1, J2 M2, and I won't use a double braces for that, just to show you that this is the uncoupled basis set. So this would be half. If I want M equals 1, then this should have come from M1 equals half and M2 equals half. So this is an example of the uncoupled basis set, and indeed we would have gotten this coupled basis state in terms of the uncoupled basis state by using half comma half for J1 and M1 and half comma half for J2 and M2. We wrote it in compact notation, and I simply said that 1 comma 1, the first entry being J, the second entry being M, was simply half half, half half. 1 comma 0 had a combination. I could have started with M1 equals half and M2 equals minus half, or the other way around, and we showed that this was 1 by root 2 half half, half minus half, plus half minus half, half half. So this was 1 comma 0, and 1 comma minus 1 was another stretched case which simply came from M1 equals minus half and M2 equals minus half. There was the other state which was the spin singlet state. This is J and that is M. The states that contributed to the spin singlet state, the states that were superposed in order to get the spin singlet state, were precisely these states, except that the combination was different, and we got to a point where we said that we could write this in the following fashion. Minus of half minus half, half half. So this is what we had. There is a relative negative sign, and that's what is important. I could have started with this having a negative sign and that state coming with a positive sign in front of it. It won't have mattered. I stick to a convention and keep that during a particular exercise, or when I work out a single problem, I stick to a certain convention. The convention will be best demonstrated when I do more examples. I want to comment a little bit about the importance of the results that we have got. The best way, in my opinion, to understand this is by looking at the world of elementary particles. So, elementary particles are labeled by quantum numbers. In other words, they are represented by states in an appropriate linear vector space. The state labels are various quantum numbers corresponding to the elementary particles. Examples of elementary particles, of course, could be protons, neutrons, the pions, the charged pions and the neutral pions, the kaons, the charged kaons and the neutral kaons. By that I mean the deltas, some of them, one of them is neutral and the others carry electric charge, and so on. In fact, there is a wide variety of particles, and depending upon the spin of the particle, the spin quantum number of the particle, particles are classified as fermions and bosons. Fermions are particles which have spin half in units of h cross, half integer spin, in units of h cross. So, examples are protons and neutrons, electrons. These come with little s equals half. Sz, of course, could be, or m could be plus half or minus half, that is okay. And then you have objects like the deltas. Now, these have s equals 3/2 in units of h cross. So, these are spin 3/2 particles, examples of spin 3/2 particles. Then there is pi plus, the pions, pi 0 and pi minus. The suffix denotes the electric charge. These are examples of, and there are many more particles, but these are examples of spin 0 objects. So, they are bosons. Bosons have 0 or integer spin, and fermions have half integer spins. So, spin is a quantum number which certainly is important in representing the particle. Now, apart from spin, there is another quantum number called isospin, and this is very relevant, particularly in the context of particles which can interact strongly with each other or decay strongly. The nuclear force is an example of a strong force. So, examples of objects that can interact strongly are protons, neutrons, not the electrons, the deltas, that is delta plus plus, delta 0, delta minus, of course pi plus, pi 0, pi minus. All these and many more are examples of strongly interacting particles, and strongly interacting particles are called hadrons. I want to emphasize that hadrons interact strongly and can also interact electromagnetically or weakly, as the case may be. The definition is simply that these particles are capable of interacting strongly. They could have electromagnetic interactions or weak interactions, may or may not have it. That is not the issue. The point is, hadrons are particles which are capable of strong interactions. These are examples of such particles. If you look at the proton and the neutron, so I am going to look at some of the hadrons. If you look at the proton and the neutron, for instance, of course, this carries a charge plus E, and this has 0 electric charge, it is electrically neutral. That is certainly a difference between the proton and the neutron. But if you look at the other quantum numbers, both of them have spin half h cross. If you look at their rest mass, that is approximately 938 million electron volts by c squared. It is conventional in particle physics and very useful to talk in terms of energy units, and therefore, if I convert the rest mass into energy by multiplying the rest mass by c squared, I get energy 938 MeV approximately. There are other quantum numbers which I need not introduce now. such as the baryon number, strangeness, and so on, it turns out that the proton and the neutron have the same values for these quantum numbers. And so I would like to look at it in the following fashion. Of course, I can see the difference between the charge, electric charge of the proton and the neutron if I turn on the electromagnetic field, because a charged particle deflects in the presence of an electromagnetic field. In other words, it interacts with the field quanta, the photon, and exchanges momentum and energy with it and deflects in its track. A neutron does not do that because it is electrically neutral. But suppose I did not switch on the electromagnetic field at all. If I were only considering a world of strong interactions and not anything else, not the electromagnetic force or relatively negligible forces like the weak force and the gravitational force, suppose I did not consider any of that. In a world of strong interactions, there is no way of seeing the difference between a proton and a neutron, because I cannot see the difference in their charge, electric charge, since I am not using the electromagnetic field at all, not switching it on. In other words, I am not considering the fact that the proton can interact electromagnetically with itself. For instance, two protons can interact electromagnetically and two neutrons cannot. A neutron cannot interact electromagnetically with a proton. Suppose I did not talk about electromagnetism, I cannot see the difference between the proton and the neutron, because all other quantum numbers are the same and the rest masses are approximately the same. Now, you could always tell me that I can see the difference in the rest mass. I could, but now it is known that this difference, this small difference in the rest mass of the two particles, really arises from the fact that the protons can interact electromagnetically and the neutrons cannot. Therefore, if I switch off the electromagnetic field, I do not see the difference between the proton and the neutron. I could think of them as two states of a single object called the nucleon. I could think of the proton and the neutron in a world of strong interactions only as a doublet, the nucleon doublet, the proton being one of the states of the nucleon and the neutron being the other state of the nucleon. And then it turns out that there is a new quantum number which can be associated with these objects, and that is called isospin, to distinguish it from the spin that I have been talking about, or orbital angular momentum. And a third component of isospin, you could call that Iz or I3, and that is the analog of m, s comma m. So I could label the proton and the neutron as a doublet with a certain value of I and Iz. This is another value of I and Iz. These are the isospin states of the proton and the neutron. I would give entries I and Iz for the proton and the neutron. Isospin is analogous to spin in the sense that there are three generators, three Hermitian generators of isospin. I would call them Ix, Iy and Iz. These are Hermitian operators and they satisfy the isospin algebra, which is the same as spin. And therefore, it follows that all that I said about spin or angular momentum can be now told in the context of isospin, simply replacing j by I, which means jx by ix, jy by iy and jz by iz, little j by little I, because I squared acting on a state Iiz is I times I plus 1 Iiz, and Iz, the operator Iz, acting on a state with labels little I and little Iz. Give me this. It is evident that I squared and Iz commute with each other, and that is why I am able to do this. Now, getting to this, Like a spin doublet, I could treat the proton and the neutron, since there are only two states of the nucleon, I could treat the proton and the neutron as an isospin doublet, the proton being in the I is equal to half and I3 equals half state, the neutron also being in the I is equal to half and I3 equals minus half state. This is analogous to the spin doublet. You could think of the electron in the up state as a spin half, m equals half state of the electron, and the electron in the down state as an s is equal to half, m equals minus half state of the electron. Similarly, I talk of an I equals half, Iz equals plus half state, and an I equals half, Iz equals minus half state. Of the nucleon, the half comma half state is the proton and the half comma minus half state is the neutron. It is not merely the protons and the neutrons that form isomultiplets. It turns out that all hadrons form isomultiplets. These objects, delta plus plus, delta 0, delta minus, happen to be an isoquartet. In other words, they are 4 states, they are a set of 4 objects that transform as an isomultiplet. So they transform analogous to a spin 3 by 2 object. This would be an I equals 3 by 2, Iz equals 3 by 2. This is an I equals 3 by 2, Iz equals half state. This is an I equals 3 by 2, Iz equals minus half state, and this is an I equals 3 by 2, Iz equals minus 3 by 2 state. So I have an isoquartet, and therefore I is fixed. It's a single multiplet where isospin is 3 by 2, and Iz takes values minus I to plus I in steps of 1. Now if you look at the pi plus, pi 0, pi minus, they transform as a triplet under isospin. So indeed I have pi plus, which is the I equals 1, Iz equals 1 state, pi 0, I equals 1, Iz equals 0 state, and pi minus, which is I equals 1, Iz equals minus 1 state. Isospin and Iz are 2 labels like the charge or like the spin of a particle. They are quantum numbers corresponding to a particle, and 2 particles will differ at least in 1 quantum number. These are just examples of quantum numbers which label particle states. In any case, that was a digression, but in the context of what I have done here, I could think of this whole exercise as being done in the context of combining 2 isospin equals half objects. In other words, I could think of this as I1, the isospin of the first particle, and that as I2, the isospin of the second particle. As I said, this is possible because isospin follows the same algebra as angular momentum, or orbital angular momentum, or spin, and therefore I simply have to replace j by I, jz by Iz, and carry on for bookkeeping purposes. So returning to this problem, I have the following situation. Suppose I had 2 beams interacting strongly. One is 2 beams of nucleons. So beam 1 has protons and neutrons, beam 2 has protons and neutrons. Now when I look at it as a coupled system, as a composite system of 2 nucleons, of course if I think of them as protons and neutrons, the proton state is half comma half, as I have just now explained. The neutron state is half comma minus half. This is the uncoupled situation where I think of them as independent subsystems. But I could think of 2 protons, one from beam 1 and the other from beam 2. Now if I did that, it would be represented by half half with half half. This is beam 1 and this is beam 2. If you wish, you could call this beam A and that as beam B. Now I could think of 2 neutrons, and that would be a half minus half, with a half minus half. These are basis states in the uncoupled basis. Of course, I would use my shorthand notation and just call this half comma half semicolon half comma half. So that will be like I, Iz, I1, I1z, I2, I2z, and so on. So that is analogous to J1, M1, J2, M2. But I could think of them as a coupled state. So for instance, I can have protons from the first beam interacting with protons from the second beam. That is the initial state, to give me a final state of 2 protons. So the possibilities are the following. The question to be asked is, how do I couple 2 I equals half objects, and what is the coupled state? As you know, the coupled states are 1, 1. So this is I, Iz in the coupled basis. That is my notation, because I am not able to put it in bold as a bold ket, and therefore I do this. So the uncoupled basis states would be half, half, half minus half, 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 half. But that is like combining 2 protons, and therefore this would just be identical to the statement that in the uncoupled basis I have 2 protons. In the coupled basis, that amounts to an I equals 1, Iz equals 1 state. Then I have I equals 1, Iz equals minus 1 state in the coupled basis. This should have come by working with I1z equals minus half, I2z equals minus half, because I could have got Iz, the z component in the coupled basis, to be minus 1 only if I had a minus half here and a minus half there. This is simply analogous to M equals M1 plus M2, and that is like saying that I have combined 2 neutrons. So I could have written this. But I can also have a situation where I can have I equals 1 with Iz equals 0, and that could have come by taking a proton from the first beam, combining it with a neutron from the second beam, or by taking a neutron from the first beam and combining it with a proton from the second beam. And this is my notation. This is for the first beam, second beam, first beam, second beam. But these are different states, because this is A times half, half, half minus half, plus B multiplying half minus half, half, half. But we had worked out these CG coefficients earlier, and we know that 1, 0 is simply 1 by root 2 NP plus Pn. The singlet state 0, 0 is orthogonal to this state, and we could have written that and we showed that this is 1 by root 2 Np minus Pn. In the language of protons and neutrons and isospin, this is what it is. Earlier on, I had written it in terms of J and M in the following manner. So if I call this I and I call that Iz, that is a proton neutron minus neutron proton. Well, I have written neutron proton minus proton neutron here, but as I said, it's the relative sign that's important, and I have pulled out a 1 by root 2 and put in a relative negative sign. So this is the singlet state of isospin, and these are the triplet states of isospin. Now, given these, I ask the following question. Suppose I look at the process, proton-proton interacting strongly to produce 2 protons. Experimentally, what the experimenter observes in the laboratory is the cross section for this process, the scattering cross section for 2 protons interacting to produce 2 protons strongly. Now, if that is what I was looking at, I compute the scattering cross section in 2 stages. First of all, there is a scattering amplitude which I will denote by S initial state to final state. This is an operator. It depends upon the interaction Hamiltonian. I could just call it SFI. So this is an operator, and this is the matrix element which takes it from an initial state to a final state. So in this context, I have the scattering amplitude for PP going to PP, and that's the same in my notation as this object. In other words, I have to find out what is the probability that if I started with the combination 1, 1, I end up with the same combination after the interaction. I get 1, 1. Want to denote this by S 1, 1. 1, 1, that is what I put on there. The scattering cross section is essentially, apart from some constant factors which would not change for all these processes, because it is based on kinematics, it is based on the phase space available, it is based on the energy and the momentum available, and that does not change. Apart from this overall constant, this is modulus of S 1, 1, the whole square. This is a matter of derivation, but we will take this as a definition, and this is what is measured experimentally. The scattering cross section is measured experimentally. This is like an amplitude which mod squares to give me the cross section. It is the probability that two protons interact with each other to produce two protons. Similarly, I can ask, what is the probability that if I prepare a state very carefully, an initial state very carefully, with I equals 1, Iz equals 0, what is the probability of starting with that initial state and ending with that same initial state? In other words, what is the scattering amplitude for a state which is prepared very carefully as NP plus Pn by root 2, going to a final state which is also given as Np plus Pn by root 2. So sigma for this process, the scattering cross section for an initial state carefully prepared as Np plus Pn by root 2, going to Np plus Pn by root 2, is essentially x S 1, 0 mod square. Similarly, sigma Nn going to Nn, and now the notation is evident. An initial state of 2 neutrons going to a final state of 2 neutrons is S 1, minus 1, the whole square. Now, I could have prepared it in the state ket Np by root 2 minus ket Pn by root 2, which is what I have there. So, the probability S Np minus Pn by root 2 going to itself, this mod square apart from a constant factor is sigma Np minus Pn ket by root 2 going to Np minus Pn by root 2. And this is what I have. These are the various possibilities that I have, assuming that strong interactions conserve isospin and Iz. So, I will not, for instance, ask what is the probability that 1, 1 goes to 1, 0, because in strong interactions Iz is conserved, which means that the initial state's Iz value is equal to the final state's Iz value. Similarly, the initial state's isospin value is equal to the final state's isospin value, and therefore, there is nothing like 1, 1 going to 1, 0. The labels have to be the same in both cases. So, these are the only possibilities. Now, I find something interesting. I know that I cannot see the difference between the proton and the neutron. This is an I equals half, Iz equals half. This is an I equals half, Iz equals minus half. in a world of strong interactions. So given an isomultiplet, that means once you fix I, changing Iz in steps of 1 takes you to various particles within that same multiplet, and with strong interactions alone I cannot see the difference between the various particles that belong to the same isomultiplet. Obviously, therefore, I cannot see the difference between 1, minus 1, 1, 0 and 1, 1, because these are all states with the same isospin value made of the same set of particles, nucleons, 2 nucleon system with I equals 1, but the Iz value changing. And therefore, I will use a shorthand notation. I will drop the third component because it does not matter, cannot see the difference between the coupled state 1, 0, 1, minus 1 and 1, 1, and therefore, the cross section can be now written in the following manner: sigma pp going to pp is an overall constant S1 mod squared. This one stands for I equals 1. Sigma nn going to nn, it's the same S1 mod squared. The only difference being that this is the 1, minus 1 state, but as I said, the second index does not matter within an isomultiplet, and sigma np plus pn by root 2, which is the I equals 1 combination going to itself. But clearly this is in general not equal to 1, 0, 0, because this is a different isospin valued object. This is an isosinglet, and that is part of the same isotriplet. What does that mean? It means the following. The cross section or the probability of 2 protons in the initial state interacting strongly to produce 2 protons, this probability or the cross section for pp going to pp is the same, is equal to the cross section for 2 neutrons interacting to produce 2 neutrons, and indeed is the same for a neutron from the first beam and a proton from the second beam, a proton from the first beam and a neutron from the second beam taken and prepared very carefully in the isospin 1 state, that is as part of the isotriplet, going to itself. So these cross sections are the same, and that is not the same in general as the cross section for the isosinglet going to itself. So if you prepared the state combining a neutron and a proton as np plus pn by root 2 going to itself, that cross section is the same as the cross section for pp going to pp or nn going to nn. But if you prepared this combination in the antisymmetric state np minus pn by root 2, by antisymmetric I mean that if you interchange the neutron with the proton, you pick up an overall negative sign. The symmetric one means that you pick up an overall positive sign, as happens here. So if you prepare it in the antisymmetric state or in the isosinglet state, the cross section is not the same as these. This is popularly called charge independence of nuclear forces, because nuclear forces, as I told you, is an example of the strong force. So charge independence of nuclear forces simply means the following: it is irrelevant whether you take neutrons or protons. The fact that the proton is electrically charged and the neutron is electrically neutral does not matter, provided you prepare the 2 nucleon system in the same isospin state. That means in the I equals 1 state or the isotriplet state. Then the cross sections are the same. The only difference that can be seen in the laboratory is because of this, because when a neutron interacts with a proton, it could be either in the I equals 1 state or in the I equals 0 state, and the small difference between these values, between this and that, comes because of this extra piece, which makes a contribution in neutron-proton interactions. This has been experimentally verified and is popularly, it goes under the name charge independence of nuclear forces. So, nuclear forces are charge independent provided we are talking about the same isospin state, I equals 1 or isotriplet. In the isotriplet state, I find that these cross sections are the same, and that is not the same as the cross section for the isosinglet going to itself. So, this is a very important and useful, experimentally verified example of addition of angular momenta, except that I have also used this opportunity to introduce a new quantum number, isospin. It is very important in strong physics, strong interaction physics, and is an important quantum number. I and Iz are important quantum numbers which label particles that interact strongly, hadrons. Now, having demonstrated this, I will go ahead and illustrate addition of angular momenta in more detail by conducting the following exercise. I will now combine a j equals 1 state with a j equals half state. In other words, the exercise is the following: j1 is 1, j2 is half. So, we are going to combine these two objects. So, j takes values 1 plus half to 1 minus half in steps of 1. So, j takes values 3 by 2 and half. Corresponding to j equals 3 by 2, m can take various values. So, let me write all the coupled states. J equals 3 by 2, so m can be 3 by 2, but m can be half. It goes down in steps of 1. M can be minus half and m can be minus 3 by 2. And if j equals half, m can be half, m can be minus half. So, these are the various coupled states that are possible in this context. What about the uncoupled basis set? So, this is the coupled basis set. Now, the uncoupled basis, that is J1 M1, J2 M2. I have half half combining with 1. So, perhaps I could write 1 1 combining with half half, 1 1 combining with half minus half, then 1 0 combining with half half, 1 0 combining with half minus half, 1 minus 1 combining with half half, and 1 minus 1 combining with half minus half. So, the labels are clear, that is J1 M1, J2 M2, that is what I have. So, I have the following 6 states. You will recall that that is 2 J1 plus 1 times 2 J2 plus 1 states, therefore 6 states. And here too I have 6 states, that is 4 of them here. This is a j equals 3 by 2 quartet, this is a j equals half doublet, and therefore I have 6 states. So, the number of basis states match, and this is a very important thing to verify when one does a calculation. So, I would like to find the CG coefficients in this context by expanding the coupled states in terms of the uncoupled basis. So, let us start with 3 by 2, 3 by 2. Remember that this really amounts to J1 is 1, J2 is half, J is 3 by 2 and M is 3 by 2. But I am dropping J1 and J2 and just using J and M as the labels for the coupled state. But 3 by 2, 3 by 2 could have come only in the following fashion. It is a stretched case because if I want m equals 3 by 2, then m1 should have been 1 and m2 should have been half. The only possibilities for m1, as you can see, are 1, 0 and minus 1, and for m2 are half and minus half. So I just have 1 comma 1 with half comma half, and this is the uncoupled basis, and therefore I do this. This is J1 m1 J2 m2. Of course, by this I mean the following: J1 m1 J2 m2, but I am going to use this as a simple way of writing it. So this is a stretched case. There is no other way I could have got 3 by 2, 3 by 2, and therefore the CG coefficient is 1, and that is a stretched case. Similarly, 3 by 2 minus 3 by 2 should have come by combining m1 equals minus 1 with m2 equals minus half. So while J1 and J2 are fixed, m1 and m2 are now minus 1 and minus half, and that is the only way I could have got 3 by 2 minus 3 by 2. Therefore, that is a stretched case. I need to find 3 by 2 half, and as I pointed out yesterday, I can do this by using J minus here, correspondingly J1 minus and J2 minus there. I need to remember the following: J minus acts on a state Jm to give me root of J plus m times J minus m plus 1. I have set H cross equals 1, J comma m minus 1, and J plus acts on Jm to give me root of J minus m times J plus m plus 1, J m plus 1. These are the lowering and raising operators respectively. So I use that, and therefore when I use J minus here, the coefficient is root 3, where I have used J is 3 by 2 and m is 3 by 2. Here J1 minus acts on this, leaving that alone, pulls out a coefficient J1 plus m1 times J1 minus m1 plus 1, reduces m1 to 0, leaves J2 and m2 as such. J2 minus acts on this and leaves this alone. So J1 and m1 do not change, and I pick up a coefficient root of J2 plus m2 times J2 minus m2 plus 1, and m2 gets reduced by 1. So I have this. In other words, I can write 3 by 2 half as the state root of 2/3 1 0 half half plus root of 1/3 1 1 half minus half. So this is what I have. I need to get the state 3 by 2 minus half in terms of the uncoupled basis. It's worth pointing out that the mod square of the CG coefficient summed together gives me unity. That's a 2/3 plus 1/3, and this is a thing that needs to be checked out. Further, if I want a half here, that's a 0 plus half, and that's a 1 minus half. These are things that should be checked out at various stages. So if I want to do 3 by 2 minus half, I can use J minus on this. Well, there are two terms and a little bit more work to be done. I could have done a J plus on this. That's just one term on which I need to work. So if I use a J plus, I remember that the coefficient here is J minus m times J plus m plus 1. So I have this, and here I use J1 plus, which is a J minus m times J plus m plus 1, takes 1 comma minus 1 to 1 comma 0 and leaves the other state as such. Then I have J2 minus acting, J2 plus acting on this. It leaves 1 comma minus 1 alone, and pulls out half plus half times half minus half plus 1, and then takes minus half to plus half. In other words, 3 by 2 minus half is root 2/3 times this plus root 1/3 times the other state. So I can write this as root of 2 by 3 plus root of 1 by 3. Once more, it is clear that things add up. Root 2/3 square plus root 1/3 square is 1. So I have the various states here. These are the stretched cases, and then I got these by using J minus and J plus. So I have already written these 4 states in terms of the uncoupled basis. I need to find half comma half and half comma minus half. Now I do the following. Consider the state half comma half. This is J and that is M. Half comma half is like 3 by 2 comma half in the sense it has the same uncoupled states contributing to it, 0 plus half and a 1 minus half, but the coefficients would be different. So I write half comma half as A times 1 comma 0 half comma half plus B, that is the coefficient, and I have 1 comma 1 half comma minus half. Given the fact that A squared plus B squared is 1, I need to determine these CG coefficients. This is easily done because this is one equation. The other equation is this: 3 by 2 half is orthogonal to half half. Of course, all these states are orthogonal to half comma half, but what is of relevance is the fact that 3 by 2 half is orthogonal to half half, because in the uncoupled basis they are superpositions of the same states, and this implies that root of 2 by 3 A plus root of 1 by 3 B equals 0, or B is minus root 2 A. So I can use that, and so I have A squared plus B squared, and that gives me a 2A squared. So I have 3A squared equals 1, which gives me A is plus or minus 1 by root 3, which tells me that B is minus or plus root of 2 by 3. This is where I can use the convention. I am going to look at the second state and look at the M values. Well, this has a higher value compared to that, so my convention is to put a positive sign here and a negative sign there. I stick to this convention throughout the problem. So I have half comma half is minus 1 by root 3, 1 0 half half plus root of 2 by 3, 1 1 half minus half. Again, the mod squares when summed over add to 1, that is a 1/3 plus a 2/3, which gives me a 1, and that is what I have for half comma half. I could have written plus 1 by root 3 here and a minus root of 2 by 3 there. As I said, I have used this convention. We can get half comma minus half in 2 ways. We can use the fact that half comma minus half is orthogonal to 3 by 2 comma minus half and repeat the procedure, or can use a J minus on this and get half comma minus half. So that gives me a 1 half comma minus half minus 1 by root 3 is fixed. J1 minus acts on this, leaving this alone, plus J2 minus acts on that, leaving this alone. Similarly, plus root of 2 by 3, J1 minus acting on this, leaving that alone, and J2 minus acting on that, leaving this alone. And once that is done, we have the state half comma minus half, which can be simply found out. That is one way of doing it. As I said, the other way is to use the fact that half comma minus half is orthogonal to 3 by 2 comma minus half and find out the coefficients, which too can be done. But remember the convention. I compare the second entries And if M2 there is smaller than M2 here, that comes with a positive sign and this comes with a negative sign. I stick to that convention during the problem. I leave it to you to complete this exercise.